Hello everyone and welcome to my tutorial on polynomials and algebraic division. If you're new to my channel, I create videos on tutorials of key maths topics that aim to help with learning and revision. Today we're going to be looking at polynomials and in particular algebraic division, as this can be tricky. Let's start with some key terms for polynomials. A polynomial is a type of maths expression that consists of variables, coefficients, and exponents, and it is combined using addition, subtraction, and multiplication. In front of us then, we have an example of a polynomial. This has 5 terms, and in this particular example, the entire polynomial is combined using addition, but that doesn't necessarily need to be the case. So an example with some numbers. Here we have 3 plus 5x minus 7x to the power of 4. Just revising some basic terms, the degree of a polynomial is the highest power of x in that polynomial. So in our example above, the degree would be 4 because we've got x to the power of 4. The term is one of the powers of x. So 5x is one of the terms. This example here, there are 3 terms. In the generic example above, we have 5. And finally, the coefficient of x to the power of r is the number multiplying x to the power of r. In the example above then, the coefficient of x to the power of 1, which we just write as x, is 5, and the coefficient of x to the power of 0 is 3. Some of the simplest manipulations of polynomials is adding or subtracting. For example, let's say we have 2 polynomials, p of x and q of x, and you can see the expressions above. When we're adding or subtracting, for both manipulations, we consider each power of x separately. Therefore, if we're adding the polynomials together, p of x plus q of x, take each power individually. So we would start with x to the power of 5, and then we would look for in the equations for anything with the power of 4, which we only have one expression in p of x. So the beginning of our addition is 7x to the power of 5 minus 2x to the power of 4. We then look at x to the power of 3, and we have a plus x to the power of 3 in q, but we have negative x to the 3 in p. If we add those together, they cancel each other out. So we don't actually have any powers of x to the 3 in our final result. And then we have to add together x to the power of 2, or x squared. We add the 2 terms, so 2x squared plus 5x squared gives us 7x squared, plus there's only 1x to the power of 1 plus 3. It's exactly the same approach for subtraction. The only thing to be aware of is that in addition, the sum of p of a function of x plus q as a function of x would be the same as q of x plus p of x. Whereas in subtraction, the order, so which equation you are subtracting from which, makes a difference. If we are doing p of x minus q of x, we would have negative 7x to the 5 minus 2x to the power of 4 minus 2x to the power of 3 minus 3x squared minus x plus 3. But if we are doing q of x minus p of x, all of the terms are flipped. So that's something to be aware of. In addition, it does not matter. In subtraction, it does. But those are probably the more straightforward manipulations of two polynomials. Multiplying polynomials is a bit more tricky because you have to multiply each term within one set of brackets by each term within another set of brackets. And it can be quite easy to miss out a combination. In this example, what I've tried to do to show this is highlighted in the second bracket 2x squared in green and then the -1 in blue. When I multiply this out, and this is similar to in quadratic equations, a method called the FOIL method. So first, outside, inside, last, if you've heard of that. That's trying to show the same process as this. Taking one term in the bracket on the right, I have to times 2x squared times x squared, which gives me 2x to the power of 4. And then multiplying the 2x squared by minus 4x. So that gives me minus 8x cubed plus 7x times 2x squared gives me 14x squared. So I've now taken all of the pairings, if you like, of 2x squared, but it's important then to go back through and do the same process with the -1. So we have minus x squared plus 4x cubed, sorry, plus 4x. You've got a negative times a negative, which becomes a positive, and then -7. Once I have multiplied each term out, I can then look at the powers of x and start to combine them and order them. You can go in ascending or descending powers of x. I generally find it easier to do descending powers of x. We have 2x to the power of 4. Then there's only one x cubed, so minus 8x cubed plus 13x squared, because you've got plus 14x squared minus x squared plus 4x minus 7. And that's the end. If we just do one more example, this time, exactly the same concept, but in our first expression, we have 4 terms this time. Then we multiply again one set of multiplications, and then we do the second set of multiplications. So here, just trying to show the difference between the green and the blue, go 2 times 1 plus 2 times 2x plus 2x squared minus 2x cubed, and then do exactly the same process, multiplying everything in this left-hand bracket by 3x, and we get 3x plus 6x squared plus 3x cubed minus 3x to the power of 4. And now that we have a full set of terms, we can then start to combine them based on their powers. This time I've gone in ascending order. So 2 plus 7x plus 8x squared plus x cubed, because we have 3x cubed here and negative 2x cubed here, and then minus 3x to the power of 4. A little bit more tricky than adding or subtracting polynomials, but as long as you take each sequence in turn and make sure you don't skip any multiplications out, then you should be fine. It's just a case of, I would say, noting each individual calculation and then combining based on powers of x. Division then, the most tricky operation of polynomials. I think it's best to start by revision of some key terms. So we have quotient and remainder. And this is where, when we are dividing a number or dividing an expression, we are dividing with a result that has integers or full numbers at the end. So this is not necessarily where you are using a calculator to divide and you would then have a result in multiple decimal places. This is just keeping to whole numbers. So divisor is the thing you are dividing by. Quotient is the result you get when you divide that number or function by the divisor, but excluding the remainder. And remainder is the balance that you have left over. Just putting this conceptually with some numbers to begin with. As an example, 47 divided by 9 would be 5 remainder 2. So 9 is the divisor, that is what you are dividing by. 5 is the quotient, and 2 is the remainder. Bringing back to times tables, 5 times 9 is 45, but we have 47 in our example. We're not going to divide the 2 by 9 to get a partial number. We're just going to leave it as 5 remainder 2. And this can alternatively be written as 5 plus 2 over 9, or 47 equals 9 times 5 plus 2. So hopefully a useful recap of quotient and remainder. And this then becomes helpful when we are solving algebraic division. So using the quotient and remainder principle, we've got a question here of divide x squared plus 3x plus 1 by x minus 2. Just a reminder, we're looking to solve for a quotient and a remainder in this example. And one way you can express this is as a fraction, as in the previous example with numbers. So we have x squared plus 3x plus 1 divided by x minus 2. Our quotient will divide neatly by x minus 2, so we don't need to put a denominator there. And then we have our remainder divided by x minus 2. If we now multiply each expression in this equation by x minus 2, then we have our initial equations, x squared plus 3x plus 1. Then we have x minus 2, because we've multiplied each term. And then we're solving for ax plus b, and then there's going to be a remainder. So in this example, we have ax plus b, and these are like placeholder numbers. We may not necessarily have x to the power of 1 and x to the power of 0 in the final result, but we're just putting placeholders in here for now. But you would guess that if you have x squared divided by x, you're going to have x to the power of 1 in your result. And using the multiplication steps mentioned earlier, we can expand the brackets to give an equation on the right of ax squared plus bx minus 2ax minus 2b plus r, which we can then rewrite as ax squared plus x b minus 2a minus 2b plus r. And this is quite useful because the structure of the polynomial on the left is now the same as the structure of the way we've written the polynomial on the right. And this allows us to compare the coefficients and solve. Therefore, for x squared, we have in the equation on the left 1x squared, and this is equal to ax squared on the right. Therefore, a has to be 1. Similarly, for x, in the equation on the left, we have 3x, and on the right, we have x b minus 2a. We know, having solved for x squared, that a equals 1, and so b equals 5. Continuing then and comparing the constants, 1 in the equation on the left is equal to minus 2b plus r, which equals negative 10 plus r, and therefore r must be 11. Thus, if we divide our polynomial x squared plus 3x plus 1, we get a quotient of x plus 5 and a remainder of 11, which we can also write in this format. Taking another example of this time we want to divide x cubed minus 2x squared plus x plus 2 by x plus 1. So to solve, again, we want to state this in terms of a quotient and a remainder. We use the same approach as before, but this time we have a polynomial of degree 3 because there is an x cubed included. And so this time we're solving for a, b, c, and r. That said, the method is the same. So we want to rewrite the equation on the right in the format of ax cubed plus x squared b plus a plus x c plus b, and then the constants plus c plus r. We take the same approach and compare the coefficients. On the left, we have 1x cubed, so a must be 1. For x squared, minus 2 equals b plus a, and we have solved a, which we know to be 1. Therefore, b must be minus 3. For x, 1 equals c plus b, so c equals 4. And then for the constants, 2 is equal to c plus r, which is equal to 4 plus r. Therefore, r must be minus 2. For this polynomial, then, if we divide x cubed minus 2x squared plus x plus 2 by x plus 1, we have a quotient of x squared minus 3x plus 4 and a remainder of minus 2, which is our answer. Okay, so another method for doing algebraic division, which you may use or be tested on, is long division. So long division can be quite tricky as a technique. So I think it's best to start by using some numbers as a recap. If we want to divide 3,252 by 15, you'll remember that we start by putting the number we want to divide underneath the bridge. We then have our divisor on the left, 15, and then we work through it. We always take the first part of the number and we look for multiples of 15. We have 30 here. If we divide 30 by 15, that gives us 2. So we put the 2 on the top, and then 32 subtract 30, you bring down the 2, and then you bring down the 5, right? Which is the next line in the number, and that gives us 25. This time we can only have 15 in once. So you would have 1 times 15 plus 10 left over. So we subtract and we bring down the 10, and then as before, we carry down the 2. So that gives us 102. We have 6 times 15, which is 90. 102 subtract 90 is 12. We put the 6 up here. So quotient is 216 and remainder is 12 in this example. We can take a similar approach with algebraic division. So in our example, we have divide 3x squared minus 5x plus 7 by x minus 4. We place our expression in the long division box and we put the divisor to the left. Okay? Now, if we're dividing 3x squared by x, then we're going to have 3x as our term. So we put the 3x at the top. And if we, again, reverse that, so we have 3x times x, that gives us 3x squared. But our divisor is x minus 4. So what we have to remember to do is also multiply the 3x by the minus 4. And that gives us minus 12x. So we place the minus 12x here. And then we take the same approach as if we were using numeric division. So we have minus 5x minus 12x. And if you are subtracting a negative number, you get a positive number. Okay, so we have 7x here. And then, as before, we bring down the 7. So we now have 7x plus 7 that we are dividing by x minus 4. Well, if we've got 7x divided by x, that gives us 7. So we place the plus 7 here. But remember, it's x minus 4 times 7. So we have 7x minus 28. And then we do the same as previously, which is to subtract negative 28 from plus 7. And that gives us 35. So for this question, our quotient is x plus 7, and the remainder is 35. So that's quite tricky, and this may take a couple of examples of practice to get used to this methodology. Let's try another one. This time we have x cubed plus x squared minus x plus 1 divided by x minus 7. As before, we put the expression that we want to divide in the box and the divisor on the left. We want to divide x cubed by x minus 7. So we must have x squared in our result. And then we multiply that back. So we've got x squared times x, which is x cubed, but we are dividing by x minus 7. So we also have minus 7x squared. So minus 7 times x squared. We then draw a line and we subtract the terms. Plus x squared minus negative 7x squared gives us 8x squared. And we bring down the x, so negative x. Now we have 8x squared minus x, which we are dividing by x minus 7. We need to have 8x in our result because x times 8x gives us 8x squared. And then we have to times the negative 7 by the plus 8. And that gives us minus 56x. We then subtract. So negative x minus negative 56x gives us a positive 55x, and then we bring forward the plus 1. So we're now doing 55x plus 1 divided by x minus 7. Well, we would divide by 55, right? So we put 55 up the top, and then we have 55x here. So 55 multiplied by x, but we've got to do it by the full expression. So we do minus 7 times 55, which gives us minus 385. And then we subtract as well. So 1 minus minus 385 gives us 386. So therefore, if we divide x cubed plus x squared minus x plus 1 by x minus 7, our quotient is x squared plus 8x plus 55, and our remainder is 386. In all previous examples, we have had a quotient and a remainder, and you may well get a question on that. But perhaps what is more useful is when you can find a factor of a polynomial, the factor theorem. If the remainder is 0 when you divide a polynomial f of x by x minus n, then x minus n must be a factor of f of x. And this means if f of x is a polynomial and f of n equals 0, then x minus n is a factor of f of x. And factors of an equation are also called roots of an equation. So let's see an example of this and how this works. Show that x plus 3 is a factor of x cubed minus 2x squared minus 11x plus 12. F of x is the expression that we have. We therefore do f of minus 3. So n in this example is minus 3 because we have x minus n would be a factor, right? So minus positive 3 is minus 3. If we substitute minus 3 in, that gives us minus 27, minus 18, because you have x squared, which is 9. Any positive power of a negative number will always be positive. So minus 3 squared is 9, but times by minus 2 gives negative 18, plus 33, because you've got minus 11 times minus 3, plus 12. And that gives minus 45 plus 45, which equals 0. And therefore, because when you substitute minus 3 into the polynomial, the result is 0, you say that x plus 3 is a factor by the factor theorem. Hence, factorize this expression completely. What we mean is to break this down into brackets in its entirety. Well, we can use the the algebraic division that we used in previous examples. So as before, we put the expression that we're dividing by in the box, and the dividers are on the left. We're dividing by x plus 3, so x cubed divided by x is going to give us x squared. But we multiply that back out, so we have x cubed, and then plus 3 times x squared gives us 3x squared. We then subtract minus 2x squared minus 3x squared gives us minus 5x squared. And we bring down the 11x. And then we divide again. So we're dividing minus 5x squared minus 11x divided by x plus 3. So we would have minus 5x, and then we multiply that out. So minus 5x squared gets rid of that. And then minus 5x times 3 gives us minus 15x. We subtract, and that gives us 4x plus 12, which, if we divide 4x by x, gives us 4. So we add that to our expression, and we multiply out. So 4 times x plus 3 is 4x plus 12. And this time, unlike in the previous examples, the remainder is 0. Okay, we know that x plus 3 is a factor. This time we want to solve our expression for 0. And this means that x plus 3 multiplied by x squared minus 5x plus 4 equals 0. And we now have an expression that is more straightforward because we have a quadratic here. And we have a quadratic that can easily be expressed in terms of 2 more factors. I will do a tutorial on quadratic equations, but if you break this down, x squared minus 5x plus 4 can be expressed as x minus 1 and x minus 4. So that whole expression at the top, or a polynomial at the top, breaks down to x plus 3 times x minus 1 times x minus 4 equals 0. Just pausing here for a second, if you were wondering why we had in the factor theorem x minus n, and then you put f of n to find the factor, it's because if x were minus 3, or if x were 1, or if x were 4, so let's take the first bracket. If x were minus 3, you would have minus 3 plus 3, which is 0 times the rest of this expression. And 0 times by anything is 0. So you only need one of these parts of the equation to be 0 for the whole equation to be 0. And to get one of these individual sections to be 0, it's the negative number of the one you've got in the bracket. So x would be 4, 4 minus 4 would be 0. So why do we do that? Well, if we are to sketch the function, if x equals a number, but f of x equals 0, so you could replace f of x with y. This is the y-axis on the chart. Every time that y equals 0, so that would be the x-axis, is a point where the function crosses the x-axis. And so if you have x equals -3, then y equals 0. So you have -3, 0 as a point on the graph. And then similarly, when x equals 1, y equals 0. So 1, 0 is a point on the graph. And then when x equals 4, 4 minus 4 is 0. So y would be 0. So 4, 0 is also a point on the graph. And you can mark these. Any polynomial that's cubed has this shape if x cubed is positive. And that allows you to draw the function. Okay, so finally the remainder theorem. The remainder theorem states that if f of x is a polynomial and f of x is divided by x minus a, then f of a equals the remainder. So we have already seen this in a different format previously in the tutorial. But taking an example, so find the remainder f of x, for f of x, when it's divided by x plus 4. So what we can do is we can substitute minus 4 into the equation. Minus 4 to the power of 4 times 2 plus minus 4 to the cubed minus minus 4 squared plus 2. And again, remembering that a negative number to a positive power gives a positive number. So here we have 2 times 256 minus 64 minus 16 plus 2. And that gives 512 minus 80 plus 2. So the remainder is 434. So if you are given the number to divide by, you can substitute in and you can find the remainder very quickly. Now this won't tell you the quotient, but it will, if you're just asked in an example to give the remainder only, that is a faster way of solving. So some other examples. Find the remainder if x cubed plus 2x squared plus x minus 3 is divided by x minus 2. We would substitute 2, so the function of 2, which gives us 2 cubed plus 2 times 2 squared plus 2 minus 3, which equates to 15, so the remainder would be 15. And finally, slightly more tricky, f of x equals x cubed plus 2x squared plus k of x minus 1 has remainder of 2 when divided by x minus 1, so find k. So this time we've got a coefficient in the equation that we're trying to solve, but we have been told what the remainder is. Well, we work backwards, substituting 1 into the equation, so 1 cubed plus 2 times 1 squared plus k times 1 minus 1 gives us 1 plus 2 plus k minus 1, and that equals 2 because we're told that remainder is 2. Therefore, if we rearrange, k plus 2 equals 2, therefore k equals 0. F of x then would be just x cubed plus 2x squared minus 1. So thank you for listening. I hope this was helpful in terms of explaining or going through some examples of polynomials and in particular algebraic division. But just a summary of what we've covered: key terminology, adding and subtracting polynomials, a reminder of quotient and remainder, then 2 methods of algebraic division. So either solving using the coefficients, which we did at the beginning, or solving using long division. Then the factor theorem and how to find factors and roots, which then leads us to how to find all roots of a polynomial and sketch the graph. And finally, the remainder theorem, which is a shortcut for finding the remainder of a polynomial when divided, but won't help you find the quotient. But sometimes you will get questions just to find the remainder. So thank you for listening. If you liked this video and you found it helpful, please give it a thumbs up, and I look forward to seeing you in the next tutorial.